Hi, welcome to this video lecture on digital logic design. So, I am Dr. Neeraj Kumar Misra. In this lecture, I am going to explore the numerical problems based on Kmap, flip-flop conversions, registers, and what is the process to design a mod and counter. Okay, and then I will cover the PLA topic, and then I will move to the some important questions or competitive exam questions like a gate exam, and then I move to forward about the core company exam questions. Okay, so the main intention to prepare this video lecture to undergraduate students and also for preparation of the competitive exam or the core sector jobs. So here you will learn the complex problems based on these topics like Kmap and the flip-flop conversion and the registers and mod counter, PLA, and all these competitive or core sector job uh, questions. So without any delay, I will proceed this video lecture. So I encourage to all the participant to watch this video at the end. Okay, so the first question is here I given you some of the functions. So in this function there is some minterms and there is some don't care condition. So here you have to reduce this SOP expression by Kmap. So the Kmap is actually used for the optimization. Okay, that is used for the optimization. Okay, so here the number of variables ABCD. So these are this is the MSP and this is the LSP. Okay, so here this is a four variable K map. Okay, these 0, 1, 2, 3, this represent the minterms. So first thing is that you have to find out, you have to include this minterm in this function. So this minterms is represented by 1 in K map. Okay, this is represented by 1 in K map, and this is represented by don't care, and don't care condition is represented by X. So this value may be 0 or 1. Okay, so here we mention all these minterms and all these don't care conditions, and after that we have to form uh, some pairing. Okay, so this pairing means we form a one quad here, because if all one and don't care are participated here. Okay, so this is one quad is possible here. So in this term, what is a common term? One means this is B. Okay, so here there is okay, so the final expression is B. Okay, that is the optimized function of this expression. So that is a SOP expression. Okay, so now we move to one more complex problem that is based on the Kmap. That is based on the multiplexer. So this multiplexer is actually a 4 to 1 multiplexer, and here it is clearly mentions the input line. Okay, but input line is directly not come here because there is some input C and D, and this C and D is processed by some logical gates like AND gate or NOT gate. So the question is, what is a Boolean expression of this block diagram? Okay, so how to proceed this question? How to solve this question? So in the given block diagram, you just see here this I naught value is actually C. Okay, and this I1 value is actually D. And if you see carefully, what is I2? So I2 value is C bar, and another input is D. Okay, so this value is C bar D. Okay, if we come on the last input, that is I3, so that I3 means here not gate means not gate process the input. So the input is C, so here you get C bar. So I3 value is C bar. Okay, so just you mention all these inputs. This is all inputs. After that, we have to write a implementation table So this implementation table will provide you all minterms. Okay, so all the minterms means all the inputs like I0, I1, I2 you write in the horizontal. Okay, and all the combinations means your input combination, because we know in the circuits the input is C and D. So here how many possibility of these two input? One possibility is 0 1, another possibility is 0 1, and then 1 0 and 1 1. So this 0 0 represent means C bar D bar, and this represents C bar D, and this represent C D bar, and this represents C D. So these combination means we have to write here, and these are the minterms. Okay, these are the minterms 0 1 2 3. This is the minterm. So if you see here in this first expression, that is I0 value is C. That means here how what is the possibility you get C value? Okay, so in the first column if you check carefully, these two term represent C value 1. So that means here the minterm, whatever you select the minterm 2 and 3 only, because here in this case and in this case your C value is 0. Okay, but but we want a C value is 1. Okay, so the minterm here 2 and 3. Now we come to the next column, that is I1. So we know I1 value is D. Okay, that means this value is 1. Okay, so in which case your D value is 1. Okay, so there is two possibility here. This is one case, here D value is 1, and here also D value is 1. So this minterm is highlighted here. And if we come on the third input, so I2 value is C bar D. So that means what is the meaning here? This is 0 and 1. So this is only one case in the second row. Okay, this value is 9. So that is you have means we have to highlight here. Now the last expression I3. So I3 is C bar. Okay, so C bar is possible in two case. Okay, so finally we what are the minterm? You just circle here, same thing you write in the SOP. Okay, so these are the minterm, and this is the final answer of this question. Okay, so this problem is based on the multiplexer. Now we have to solve one more question based on the multiplexer. Here I given you some SOP expression, and this minterms I given you, and I say you have to implement this function by 6 to 1 or 8 to 1. Okay, so we know here in 6 to 1 marks the number of select line. Okay, the number of select line is 4, because here 2 to the power 4. So number of select line is 4. So here suppose that the variable is ABCD. Okay, so all the variables, because here in the function the number of variable is also 4. So that means all the variables are utilized here for the select line. That means the input, these are the input. Okay, so this input we have to select from this minterm, means this minterm 0 1 3 4 7 10 and 14. This minterms you provide a logic 1 or the VCC supply. Okay, and what are the missing minterms here? Means the missing minterm is 2 5 6 8 9 11 12 and 13. These are the missing minterm in this function. Okay, so this minterm is assumed as a logic 0. Okay, so here we provided a two logic, one is logic 1, another is logic 0. Okay, so this one is considered as a logic 1 and this one is considered as a logic 1. So this is a final expression. Okay, so this is a final expression that is denote as a output. Okay, so this output is this output is all minterm. This function provided all the minterms. Okay, so now we come to the second part. So here we implement the same function with 8 to 1 multiplexer. Okay, so the concept is very simple. In 8 to 1 multiplexer, the number we have to find out the number of select line. So number of select line is 2 to the power n. So n value is 3. Okay, so these are the select line. So I assume that B, C, and D is the select line because in the function there is a 4 variables. So one variable means the remaining variable A as an input. Okay, this as an input, and this is known, BCD is known as a select line. Okay, so the question is how, what are the minterms here? So that minterms value you have to find out from this implementation table. So these are the input combination A bar and A, and these I0, I1, I2, I4, these all represent your inputs. So we know very well all the select line, if you change the select line, flop generate the two output. Okay, one is a normal output Q, another is a complemented output, that is known as a Q bar. Okay, so all the connections you have to just mention here, and this is a complete circuit. Okay, and this is the conversion of JK to SR. Okay, now we come to the one more question. That question is based on the register. So we know the register is a combination of flip-flops. Okay, and this register is actually a synchronous type, means one a single clock is required to shifting the data. So all clock is connected to all the flip-flops. Now we just read this question very carefully. So there is a 4-bit shift register. Okay, that is correct because this is a 4-bit shift register. This is one flip-flop. Okay, this is another, and this is third, and this is fourth. Now the question is here, shift the bit on right on every clock pulse. Okay, so initially here all the data is stored here. Okay, so what is the data here? 1000. Okay, this data is already stored in the all flip-flops. Okay, so this all flip-flop is designed by D flip-flop. Okay, it is already mentioned here. Don't worry, this is all flip-flop. Okay, this is also D, this is also D, and this is also D. Now here there is some logical gates, that is one XOR and one XOR. So D output is not normally connected. This output is connected by two cascaded XOR. Okay, so this is Q3 and this is Q2, and this XOR generate this right side XOR generated Q2 XOR Q3. Okay, and now we come to the right hand side XOR gate. Here your input is Q0. That means this first XOR, this is second XOR. Okay, so this second XOR generate the output Q0 XOR Q2 XOR Q3. Okay, so this is actually D. Okay, this is actually D. Q0 XOR Q2 XOR Q3. Okay, now all the data are there. We have to apply the clock and shift the data. Okay, but the question is how many times we have to shift. Okay, so that is a question, means how many times you have to apply the clock, you get the same pattern in the flip-flop. Okay, okay, so now we have to proceed in this way. Initially we are not applying any clock, and the data, there is no data. Okay, but initially all the flip-flops has stored some data. It is already stored some data 1000. Okay, fine. Now here one condition is that this value is already stored in all the flip-flops. Okay, in first flip-flop, second flip-flop, third flip-flop, and fourth flip-flop. Now we are going to apply the clock. Suppose that if we apply one clock, so what is D value? Because the first value D is defined by this expression. Okay, so we know Q0 value, just see here. So your q naught value is 0. Okay, q naught value is 1. Okay, q naught value is 1 and q2 value is 0 and q3 value is again 0. So that means 1 XOR 0, 0 XOR 0, that means here 1. So now we get d value 1 here. Okay, we get successfully d value here. If d value come here, that means this data is shifted. This data to be shift. Okay, this data to be shift. This data to be shift here on the right side. Okay, so this green color line represents the shifting of data. And this q naught value is nothing, it is d only. Okay, so how to find out d? D is find out from this expression. Okay, so this is the first clock. But they said in the question it is given you have to for shifting of data means initial data you have to get. So again we apply some clock. So we have to find out d value. So d value find out from here q naught, q2 and q3. So we get d value is 1. Okay, so this d value is come here and this shifting start on the right side. Now in the second clock your data is 1110. Okay, 1110. So again we apply the clock because this process to be continue. Now this time your in the previous data is 1110. So now we have to find out d. So d value is q naught, q naught value is 1 and q2 value is 1, again q3 value is 0. So 1 XOR 1 XOR 0 means it is 0. Okay, so this 0 come here. Okay, so this d value is stored in the q naught and the remaining data is shifted. Okay, remaining data is shifted on the right. Okay, so same process you apply again one clock and here this time d value is 0. So this 0 value come here and the data is shifted on the right. So same process to be repeat. Again we apply one clock and this time your d value is 0. Again this 0 come here and the shifting process is going on the right side. And if you come in the sixth clock, the d value is 1. This 1 value is come here and this 0 0 shifting on the right side. Now if you check carefully here, this data, what are the data is stored here 1000. That is your original data. Okay, that is your original data. So what is the observation here? In the sixth clock, you get your original data. Okay, you get the original data. So that is the answer. In the sixth clock you get the original data. Okay, now if you come in the second part, so here the pattern is already defined 1001. Okay, so what is 1001? So this d value is 1. Okay, d value is 1 and q naught value is 0 and q1 value is 0 and q2 value is 1. So the question is what is uh, the data in the flip-flops. So we do not know what is q3. Okay, so but in the logical circuits we know the d value. D value is q naught XOR q2 XOR q3. So just we put here d value, q naught value here and okay, and q2 value here. Okay, but this q3 value we do not know. Okay, so in this expression LHS must be equal to RHS. So there is only possibility if q3 value is 0. Okay, so ultimately we get q3 value is 0. Okay, so now your data means what is output is q naught, q1, q2 and q3. So q naught we know 0 and q1 we also know 0. Okay, and q2 value we also know 1, but q naught value we have already find out here, this is 0. So that is the output. Okay, that is output. So this data is stored in the flip-flop. If you apply a one clock, okay, if you apply a single clock, what is the new data in the flip-flops, in all the flip-flops? Okay, so again we have to find out the d value. Okay, so d value is q naught XOR q2 XOR q3. So what is Q naught? Q naught is 0. What is Q2? Q2 value is 1. And what is Q3? Q3 value is 0. So here we get D value is 1. Okay, so that means in the clock, this is the first clock, and this is your data. D value is 1. Okay, so this 1 is come here in Q naught, and now the shifting of data is started. Okay, shifting of data is started on the right side. So after 1 clock, the data in the all flip-flop is 1001. Okay, that is the final answer. Okay, that is the final answer. Okay, fine. Now we come to the next question. In this question, means you design up counter. So up counter means we are going from one state to higher state. Means if you go from 0 to 1, 1 to 2, okay, like that. This is a process. That is up counting. Okay. So now here we are using a mod 5 counter. So ultimately, what is mod 5? So suppose that I take a general term mod n. So mod capital N represent the number of states. So that means here 5 states. Means we have to count the 5 state. So how many states are possible? 0 to 1 and 1 to 2 and 2 to 3. Okay, one more state is required. I think 4. Only 5 state. So 1, 2, 3, 4, 5. Because this is up counter. We go for designing of up counter. Okay, so we have to count this state. Okay, 0, 1, 2, 3, 4. Okay, but the question is all the counter is designed by flip-flop, but we do not know how many flip-flops are required for this designing of counting the state from 0 to 1 or 1 to 2, 2 to 3 and 3 to 4. So there is a one relationship between number of state and number of flip-flops. So capital N value is less than equal to 2 to the power n. Okay, so here we know the capital N value. Capital N value denotes the number of state. So n value is 5 and this condition to be maintained. So if you put n value is 0, that means 5 less than equal to 2 to the power 0. Okay. Okay, means that is not possible because 5 less than equal to 1. Okay, so here one is not, this condition is false actually. So we take another value, n value is 1. Again, this is not possible. If you take n value is 2, again it is not possible. If you take n value is 3, okay, so 5 less than equal to 2 to the power 3. So 5 less than equal to 8. Oh, that is correct. Okay, that is correct. So that means here number of flip-flops is 3. Okay, number of flip-flop is 3. So three number of JK flip-flop you have to use in the design of up counting from state 0 to 4. So that means we have decided the state in the first step. This is the first step, and we decided the number of flip-flops. Now in the second step we go for the state diagram. So state diagram is only the transition from first state to next state. Means we are going to count from 0 to 1, 1 to 2, 2 to 3 and 3 to 4 and 4 to 0. And this is only I have written only the binary value of all these state. So after the second state we are going to implement this table. What is this table? So here all the we know the three number of flip-flops means three outputs. Okay, so the output is QA, QB and QC. This is known as a present state. And if I write QA plus QB QB plus and QC plus, this is known as the next state. Okay, this is known as the next state. So okay, fine. How to write all these value here? This is very simple. So first state is 0 0 0. Now from this is the present state. Now in the present state, what is the next state? Next state is 1. So what is one value? 0 0 1. Okay, after this state 001 you have to write here. Okay, now we go for the next state. After 1 we go for the second state. Second state is 010. Okay, now the same thing you have to write here 010. After the second state we go for the third state. The third state is 011. Okay, so the same thing you have to write here. And after the third state we go for the fourth state. Okay, fourth state is 100. Okay, after that we come to the initial state. Okay, we come to the initial state because all the counting are complete. So after 4 we go for the 000 state. But number of inputs, if you see here, number of flip-flop is 3, number of output is also 3. So this is your input. So number of combination 2 to power 3 means 8 combinations are possible here. Okay, 0 to 7. Now the problem is our counting is complete from 0 to 4 only. Okay, so remaining state means after 5. Okay, after 5 6 7 is the invalid state. Okay, so we do not know this next state, so that's why it is written as a don't care. Okay, this is written as a don't care. Okay, because after 4 we go for the 0 state, and after 0 state the counting is complete, and 5 6 7 is not, our requirement is not there. Okay, we do not count 5 6 and 7, we only count from 0 to 4, and after the reset, okay, we come to the original state. Okay, so here how to write the JA, KA, JB, KB, JC and KC value. Okay, so that is known, we know the excitation table. In 00 case means JA value, if you have to consider QA and QA plus for JA, and QB and QB plus for JB value. Okay, okay, for JB value. Okay, similarly for this is also K and this is also KB. Okay, and similarly if you consider JC and QC plus, that is for JC and KC. Okay, so this combinations you just write here, all this combination, and now this table is complete. So how to write this combination? From this excitation table we know very well. So after that we are going to find out the Boolean expression. Then our work is very easy to implement the logical circuits. So we know J value, there is some min terms and there is some don't care condition from this table. Okay, from this table we know here J value is only high. If you come here, this J value is only high if the min term is 3, because this J value is 1. So that means min term is 3 and the remaining condition is don't care. So what is the don't care? 4 5 6 and 7. Okay, this is J value. So from this table we write all these value J, K, JB, KB, JC, KC. Okay, so we go for the Boolean expression implementation. How to find out the Boolean expression? We apply the Kmap. Okay, and this is a Kmap for J, and we get J value is QB, QC. And what is K value? K value is 1, and JB value is QC, and KB value is QC. And now we come to here, JC value is QA bar and KC value is 1. Okay, so here there is a 3 variable Kmap. All the Kmap is 3 variable. Now we are going to implement the logical diagram. Okay, we have get all this expression from Kmap. Okay, that is optimized result. Okay, so here you just see carefully, this J value is QB, QC. That means this function is implemented by AND gate. Okay, and remaining there is no other gate because all these are single value. Okay, like QC and 1 and QA bar. Just take one wire. So we taken one AND gate. So in AND gate the input is QB and QC. So QB is here and QC is here. So this AND gate, the output is J. So you connect this J value from, because this is J, you have to connect here. Okay, and JB value is QC. So QC value is here because QC value is here. So that means this JB value you have to connect here. Okay, that is the only connection. This is not a complicated task. Okay, and this is the final design that is known as a mod 5 counter. Okay, number of state is 5. We are counting from 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Okay, now we come to discuss one more question, that is on PLA. Okay, so that is a programmable array logic. So in programmable array logic, means in this question they return you have to design this type of PLA. Okay, 3 cross 4 cross 2. So this is represent your input, and this is represent your product term, and this is represent your output. So we need one PLA design. Okay, we need one PLA design. In this PLA we've taken 3 input A, B, C. Okay, there may be some logical circuit inside this block. Okay, we do not know what is this circuit, and this block provided you a 4 product term. Okay, 4 product term, and you get the 2 output. Okay, you get the 2 output, maybe F1 and F2. Okay, so what is the inside block in this black box? Okay, so first step, these minterms is already given, F1 and F2. So first we have to find out the Kmap, okay, for F1 and for F2. So for F1 we get this expression, and for F2 we get this expression. Now if we consider these two function F1 and F2, there is a no common term. In this two function there is no common term. Okay, no common term. Okay, if you count the number of terms, so this is first term, this is second term, this is third term. Okay, this is fourth term, and this is fifth term, and this is sixth term. So total 6 product term in these two function F1 and F2, but we need 4 product term only. Okay, so in this way we have to find out F1 bar and F2 bar. Okay, so this two diagram, F1 bar and F2 bar, this is a Kmap actually. Okay, so what are the remaining condition? This remaining condition is the, you have to write here 0 0 0 0, the remaining block, because we are going to complement this F1 is a complement. Okay, we've taken the complement of F1, and similarly F2 is a complement here. So here we get after pairing we get two function F1 and F2 bar. Okay, so we get F1 F2 and F1 bar and F2 bar. Okay, so after that we have to write this table, because this table is very helpful to decide the 4 product term, because that is our need. We need 4 product term only. So if F1 is true, means F1 and multiply by F2, we get 6 product term. Okay, so this is not useful. And if you take in the second term, means F1, okay, means F1 is true, means F1, and okay, and F2 is false, means F2 bar. Okay, so here you check carefully, because F1 value is here and F2 bar, this is F2 bar. So there is no product term, again you get 6 product term. Okay, that is also useless. Now we come to here, if you take F1 bar and F2, so what is F1? Just we write here, F1 is AB plus AC plus BC. Oh, we have to write F1 bar, okay, not F1. Okay, so F1 bar value is B bar C bar plus A bar B bar plus A bar C bar. And what is F2? Okay, F2 value is B bar C bar plus A bar C bar plus ABC. So if you multiply this two term, so this term I think it is common, and this one is also common. Okay, so common term you consider only one. So this is first product term, this is second product term, this is third product term, and this is one more product term. So total four product term is possible here. Okay, so that function is very helpful. Means here f1 bar and f2. This function provide you a four product term. Okay, this function provided you a four product term, and here this is also useless. So what are the four terms I have written here? Do not repeat the product term here because b bar and c bar is two times, so I not consider here two times. I written here only one times. And similarly a bar c bar is also repeated two times, but I written only one time. So these are the product terms. Okay, after that we have to check the missing term. So b bar means 0 and c bar means 0, and in this term a is missing. Okay, a is missing, so we do not know what is this value. So a bar means both are 0 0. So a bar c bar means this is 0 and c bar is also 0, and here abc means all the terms is 1 1 1. So the first b bar c bar term is involved in f1 bar and also involved in f2 product f2 function. And similarly a bar b bar is only available in f1 but not available in f2, and a bar c bar is available in both the function f1 and f2, but abc term is only available in f2, only available in f2. Okay, that is known as a program table. And now here the implementation part, we are reducing the complexity, we are not taking more number of logics. So this is a NOT gate. Okay, if you apply a here, this provide you a bar. If you take one wire here, that is a. Okay, so this all AND gate is programmable. This all AND gate, suppose that this is first, second, third, and fourth. This is all programmable. Why it is programmable? Because here there is a fuse of the wire. Okay, because we need b here, b bar here, and we need c bar here. And after that, this AND gate is taken a product b bar and c bar. Okay, similarly this is a bar and this is c bar. Okay, so this AND gate taken a product of a bar and c bar. Similarly the third gate, this is a bar and this is b bar. Okay, so this AND gate provide you a bar b bar. And similarly in the fourth gate, here this is a and this is b and this is c. So this AND gate provided you a abc term. So all these product terms are available here in this wire. So we need one OR gate to select the to perform the addition operation. Okay, to perform the addition operation. Again, this is also programmable. Okay, so in the f1 expression we need three product term, and in the f2 term also we need two product term, means b bar c bar and a bar c. This is actually a bar c bar line, and this is actually b bar c bar line, and this is abc line. Okay, so this is going here. Now here you get a f1 function, but product term is generated by f1 bar. Okay, so how to take this complement? So we taken a controlled XOR gate. So this control XOR, this line is represent as a control line. Okay, this line as a control line. If the one input is another input a, so if the control signal is 0, so this signal is passing here. Okay, means you get the same output. Okay, now if okay if okay if in the okay if in the another case, if in the another case, suppose that this is one more XOR, and this time the control signal is 1 and another input is a, so that means this XOR generates a complement of this input a bar. So this type of logic we have to apply to take a complement of f1. And if the control is 0, that means the signal output signal is input signal. Okay, so this type of concept we have to apply in f2, because in f2 this is a normal input. Okay, there is no change in the signal here, f2, and here also f2. Okay, so that's why this control signal value is 0, but here we taken a control signal value is 1 because we need to take a complement of f1. Okay, so this is a complete design of PLA. Now we come to the CMOS. CMOS is known as a complementary metal oxide semiconductor. Here the CMOS is designed by two transistors. One is PMOS, another is NMOS. Okay, so in the CMOS inverter, the upper block is represented as a pull up and the lower block is known as a pull down. So most of the case, the pull down network is connected to ground. Okay, and pull up network is connected to VDD. Okay, that is the logic one, or VDD supply. Okay, this is actually VDD supply. And this pull up network, okay, this pull up network is actually designed by PMOS transistor. So PMOS transistor is P-type, okay, P-type channel. So here the PMOS symbol is like this, okay, and the pull down, okay, the pull down transistor is actually NMOS. Okay, so this NMOS is like this. Okay, this is your source, this is your gate, and this is source and drain, and this is your gate. Okay, and this is your source and this is the drain. Okay, because we know in the transistor there is a three terminal: gate, drain, and source. Okay, so this is a basic introduction about the CMOS circuits. What is pull up, what is pull down, and how to design a pull up network, and how to design a pull down network. But in the CMOS circuit there is only one output. Okay, so this output is the complement of input. Okay, so output in CMOS circuit, the output is a complement of input. That is actually a not gate behavior, because a not gate is also inverting the input signal. So same thing also in the CMOS inverter, means your if the input is something, then the CMOS inverter provided a complemented input. Okay, fine. Now we come to the designing part. So in this question we have to design a half adder circuit by using CMOS logic. So we know very well we have to design a pull up network and pull down network. So mostly in pull up pull down network there is a series and parallel connection. Okay, so how to means identify the series and parallel connection. Okay, so one concept is there in the Boolean expression. You just check the dot operation or NAND operation. This represents the series connection, and if you take if you find out any plus sign in the Boolean expression, so this represent a parallel connection. Okay, but in pull down network, because pull down network is the complement, pull down network is designed by PMOS, and PMOS behavior is opposite to NMOS, because we know very well the PMOS transistor, if the gate input is 1, that means this in if the gate input is 0, so this PMOS is on. But if you see in case of this is the PMOS transistor, but if you see in case of NMOS transistor, if the input is 0, the NMOS is off. Okay, so here one is transistor PMOS is on, but here this NMOS transistor is off. So this is a reverse behavior. Okay, so in pull down pull up down network, this connection is opposite. So first we know the expression input is the output is complemented of input. So we taken 2 times complement of S bar. Okay, and one S bar we have solved here. Okay, we have to solve here because this XOR complement is XNOR. Okay, this is XNOR, and one bar, because 2 bar is there, one bar is removed and now one bar is coming here. Okay, so this is a final expression because this x nor represent ab plus a bar b bar and whole bar. So this okay, this term, if you see here carefully, this dot sign represent the series connection. Okay, here also one dot, that means one more series connection, but this plus sign represent the parallel connection. Okay, now AB, this two series connection, again a bar b bar, again a bar b bar, this is also series connection, and after that these two are parallel connected. Okay, and we know this whole block is known as a pull down, and we know the pull down we know this pull down is designed by NMOS, and mostly the source terminal is connected to ground. So that means the source connection, this is the source, and this source is connected to ground. Okay, so this is a pull down. Okay, the opposite case formed here, because here opposite case means the dot in the pull up network, dot represent parallel connection. Okay, so a dot b, that means a dot b, this is the parallel connection. Okay, and if you come here a bar into b bar, this is also parallel connection. Okay, this is also parallel connection. So a bar b bar, this is a parallel connection. Okay, and we know in the pull up network the source is connected to VDD. Okay, because this is PMOS. So that means the source terminal is connected to VDD. Okay, and this is common point. So this common point, okay, because the pull up and pull down are connected by this wire, so this common point provided you a final expression of sum. Okay, now if you come in the carry operation, so again I taken two complement here, so just I design this part, and automatically one more bar automatically come here. Okay, because we know the behavior of inverter. Okay, so how to design this part? So dot means okay, a dot b whole bar. Okay, so dot means represent the a dot b whole bars. Okay, dot means represent the series connection. Okay, otherwise you have to convert this function in terms of okay, I will tell you. Suppose that a dot b whole bar, can we write this expression in this way, a bar plus b bar, because we know the property of De Morgan's theorem, ab whole bar is equal to a bar plus b bar. So we have to write in this way. So here plus sign, the plus sign represent the parallel connection for pull down network. So that's why these two transistors are connected in parallel. Okay, so this complete block is known as a pull down. Okay, this complete block is known as a pull down. So the inverse case is here, because here if this is parallel connection, that means here series connection. Okay, this series connection. So fine, the source is connected to VDD here, and this source is connected to ground here, and this is a common point. Okay, so this common point provide you a carry output. Okay, so this is a complete diagram of half adder. Okay, so now we come to the GATE 2023 question. So here they given you the mux 2 to 1 mux, and this is a select line. The select line value is q. Now the question is, what is y? So we know if the select line is complemented, the first input is selected, and if the select line is normal, the second input is selected. Okay, so the select line value is q. Okay, because it is already given, the select line value is q, so that is q bar. But I naught value here, the connection is ground. Okay, this ground means zero potential. Okay, plus select line value is q, and I1 value is p. Okay, so this term is 0, that means the value is qp. q dot p. Okay, so this output is q dot p. So which option is correct? So first option is correct. Okay, first option is correct. Now in the second question, this is the second question. The synchronous sequential circuit shown below. Okay, here clock frequency is given. Okay, this clock frequency is 1 gigahertz. Okay, so the question is you have to find out the latency. Okay, but here you have to find out the latency in nanosecond. But that is already given in this question, and find out the throughput in a megabyte per second, mbps. Okay, so we know the formula of latency. So latency is n times t clock. So what is n? So n is actually represent the number of flip-flops. Okay, number of flip-flops. Okay, and what is t clock? T clock value is 1 upon f clock. Okay, so f clock value is already given here. What is value? 1 gigahertz. So 1 means gigahertz means 10 to power 9. Okay, so this come in 10 to power minus 9 means it is in nanosecond. We write 1 nanosecond. So n is the number of flops. N is the number of flops means number of flop is 3. The t clock value is 1 nanosecond. So we get 3 nanosecond. So what are the possibility? The correct option is maybe this one, maybe this one, or maybe this one. This one is surely wrong because latency is 3 value only. Now we come to the throughput. Okay, throughput. So the throughput value is okay here okay that is equal to t uh, uh, okay that f clock. So f clock value is throughput value means f clock. So what is f clock? 10 to power 9 bit per second. But here they want answer in megabyte per second. So can we write in this way? 10 to power 6 into 10 to power 3. Okay, so 10 to power 6 represent the mega. Okay, mega. So 10 to power 3 means we write 30. Mega means megabyte per second. So 1000 megabyte per second. Okay, so A option is correct. Okay, because throughput is 1000 megabyte per second. So this is the last year question, GATE exam, this type of question. Okay, so one more question here. They given a circuit. So here we are using a 2 NAND gate and they ask what is a critical path delay. Critical path is actually the longest path from input to output. Okay, so but here we have to write this circuit in this way. Suppose that this is a first AND gate, this is second AND gate. So in first AND gate the input is A. Okay, another input is, what is the another input? Q bar. Okay, so another input is Q bar. We have to write here Q bar. Okay, in the second AND gate, okay, this is second AND gate. This is Q and B input. Okay, so Q. Okay, so Q, where is the Q output? Q output is generated by first AND gate. So that means we have to connect here. Okay, we have to connect here. Now what is another input? B. Okay, another input is B. And Q bar output is generated by the second AND gate. Second NAND gate. Okay, so this Q bar is connected here. Okay, fine. This is a complete circuit. Now every gate, every NAND gate has 1 nanosecond delay. So what is the longest path? So we go in this path. So in this path, this is the longest path. So this longest path is the critical delay. So in this path, there is a 2 gate, one is one AND gate, another AND gate. So the total critical delay is 1 nanosecond plus 1 nanosecond. So the answer is 2 nanosecond delay in this design. Now we come to some course company exam question. Okay, so the first question is the maximum number of flip-flops required for mod 10 counter. So in mod 10 counter, the 10 represent the number of state. Okay, the number of states. So number of state is 10. So here they find number of flip-flops. So we know the relationship n less than equal to 2 to the power n. So small n represent the number of flip-flops. Okay. So 10 less than equal to 2 to the power n. So what is the minimum value of n to satisfy this condition? So if you take n value is 3, okay, so 10 less than equal to 2 to the power 3, so that means 10 less than equal to 8. That is wrong. That is wrong. If you take n value is 4, so 10 less than equal to 2 to the power 4, that means 10 less than equal to 16. Okay, this condition is true. Okay, so number of flip-flop 4. Okay, this question is complete. Now we come to the second question. A mod 6 synchronous counter is designed by JK flip-flop. The number of count skipped it by. Okay, so mod 6 counter. So mod 6 counter means 6 state. So what is the state? 0, 1, 2, 3, 4 and 5 state. These are the 6 state. But they are asking how many skips, how many count is to be skipped. So we know the relationship n less than equal to 2 to the power n. So number of state is 6 equal to 2 to the power n. So the minimum value of n is 3. Then this condition is satisfied. Okay, we check 2 to the power 3 means 6 less than equal to 8. Okay, this condition is satisfied. So 3 number of flip-flops are required. Okay, 3 numbers of flip-flop means 3 inputs. Okay, 3 okay, I write here 3 flip-flops. That means 3 output, maybe Q0, Q1 and Q2. So how many combination? 2 to the power n, 2 to the power 3 means 8 combination. Okay, we have to check 0, 1, 2, 3, 4, 5, 6, 7. These are the state, but we have to count only 0 to 5. That means this 6 and 7 state is unused. These two state is unused in the counting process. Okay, so the correct answer is D. 2 state is not required here. So now we come to third question. In which flip-flop race round condition exist? Okay, so in JK flip-flop there is a race round condition, and T flip-flop is also. So that C option is more correct. Okay, now we come to if both input are 1, what is the next state? So that means it is a toggle condition. Toggle is represented by Q bar, so D option is correct. Okay, so I hope this lecture is very helpful for you to understand the basic concept of digital logic design. So in this lecture I cover Kmap concept and the multiplexer questions and some PLA design and some mod counter design, and also I cover some previous year gate questions and some competitive exam questions. So I hope this lecture is very helpful for you. So thank you very much for watching this lecture.